You are standing in absolute darkness, temperature dropping to 40 below zero, and you have not eaten in 7 days. The cold is not your enemy. Beneath 5 centimeters of fat and fur, your body holds steady at nearly 40 degrees Celsius. But hunger is different every day without prey. Your 250-kilogram body quietly burns through its final reserves. And across more than 2,000 square kilometers of taiga, you are the only one who knows where you are. This is the story of the largest solitary predator on Earth and what science has only recently begun to understand about the limits of its survival. The Amur tiger, also called the Siberian tiger, is the largest of the 6 surviving tiger subspecies still walking this planet. A fully grown male can stretch nearly 3 meters from nose to tail tip, weighing as much as 3 adult cattle combined. But that size is not merely grandeur, it is a weight of survival that no other land predator carries in quite the same way. The Amur tiger lives in the Russian Far East, across the Sikhote-Alin mountain range and down toward the Chinese border in one of the most remote corners of the northern world. This is temperate taiga winters lasting 7 months, snow lying meters deep, and nighttime temperatures that regularly fall below 30 degrees below zero. No other great cat on Earth lives in conditions this cold. Not the lion, not the snow leopard, not the jaguar. This creates a remarkable evolutionary paradox, a cat of tropical origins, surviving at the edge of the subarctic. The tiger's ancestors emerged from the warm, humid forests of Southeast Asia, where prey was abundant and the seasons were kind. Around 20,000 years ago, one lineage pushed northward, adapting, generation by generation, to cold that would have killed its ancestors within hours. The result is a body remade fur twice as dense as a Bengal tiger, fat reserves significantly deeper, and paws broader to distribute weight across deep snow. Even the color shifted, paler golden base, sparser stripes, and broader white on the belly and chest, lightening the silhouette against winter light. This is not accident. It is camouflage calibrated for a world of white snow and the gray shadows of leafless winter forest. Unlike tropical tigers, an Amur tiger needs a vast personal territory. A dominant male may claim between 1,000 and 2,000 square kilometers for himself alone. The reason is stark and simple. Prey density in the taiga is a fraction of what a tropical forest offers, and winter reduces it further still. And all those extraordinary adaptations solve only half the equation. The other half is prey, and that is where everything becomes far more complicated. The Amur tiger's primary prey is the sika deer and the wild boar. These two species make up more than 90% of what it eats. But unlike lions or wolves, the Amur tiger hunts in absolute solitude, no allies, no flanking tactics, just one approach and one moment that either succeeds or does not. GPS collar studies by the Pacific Institute of Geography tracked Amur tigers covering an average of 20 kilometers per night during active hunting phases in temperatures that would incapacitate a human within minutes. Success rates average only 5 to 10% per hunt, meaning 9 times out of every 10, the tiger returns through the snow with nothing. To survive a single winter, each tiger must endure dozens of failed hunts before one successful kill can balance the enormous energy debt it has been accumulating. Dale McKell, an ecologist who has spent more than 30 years studying the Amur tiger in the Sikhote-Alin Biosphere Reserve, calls this animal a living energy equation, one that must always balance. Every hunt expends energy. Every kilometer through deep snow expends energy. And every foodless day is one day closer to the threshold the body cannot survive past. Scientists from the Amur Tiger Project fitted GPS collars to more than 50 individual tigers over 2 decades, and the data that came back changed everything researchers believed they understood. The first thing the GPS data revealed was that Amur tigers do not move randomly. Each individual maintains a fixed patrol network. It repeats with remarkable precision across months and years. One radio-collared female tracked in the Bikin River Valley, retraced her own patrol route 48 times, over 2 consecutive years, returning to the same trees, the same crossings, the same ambush points. This reveals an extraordinarily detailed mental map, every trail junction, every ambush angle, every place where prey has appeared before, all held precisely in memory. The GPS data also revealed something that startled researchers. Amur tigers can move continuously for 36 to 48 hours without rest when actively tracking prey across vast distances. One GPS-collared male in the Sikhote Alin Mountains covered 70 kilometers in a single 24-hour period, with no significant rest stops recorded. 70 kilometers through deep snow, minus 20 degrees, alone, without food. And after that journey, the GPS data showed the tiger stopping near a frozen stream, lying motionless for 16 hours straight. Not ordinary sleep, but the deep rest state physiologists call maximal energy recovery, in which the body redirects nearly all its resources to cellular repair. What surprised scientists most was not the endurance of the Amur tiger, but the way it decides when to stop and when to keep moving. GPS analysis revealed that Amur tigers adjust their patrol pace and rest duration in response to hunger level, weather, and prey scent, signals with a precision that researchers had not expected from a solitary predator. When temperatures fall below minus 35 degrees, tigers actively slow their pace and extend rest periods even while hungry to prevent thermal loss that would cost more energy than the movement could gain. This is not simple instinct, it is metabolic calculation, performed at the physiological level, balancing energy expenditure against energy reserves in something approaching real time. And all of those silent calculations eventually converge on a single moment, the final approach. The Amur tiger approaches prey in a way entirely distinct from its tropical relatives, using snow terrain as a tool, not an obstacle. Rather than approaching directly, it often circles wide against the wind, sometimes walking 3 to 5 extra kilometers simply to reach the optimal attack position. Track analysis from documented Amur tiger hunts shows that on average, 75% of the entire hunt is the approach, only 25% is the strike itself. And then, at a distance of 3 to 15 meters, all that patience crystallizes into a burst of motion lasting less than 2 seconds. The Amur tiger can reach nearly 50 kilometers per hour during its final charge, but only for a very short burst before its massive body begins to overheat. This is a profound biomechanical paradox. A body optimized to retain heat in the cold becomes dangerously prone to overheating during high-intensity exertion. The dense fur and subcutaneous fat are so effective at heat retention that when muscles generate thermal energy during intense activity, that heat cannot escape quickly enough. This means the Amur tiger cannot run prey down over distance. As dogs or hyenas do, it has one short charge. And if that fails, it must wait for its body temperature to drop before trying again. The entire hunting strategy of the Amur tiger is built around one simple truth. It has one chance, and that chance must be perfect. When a hunt succeeds, the Amur tiger typically kills with a bite to the nape or throat, immediately pinning the prey with its full body weight to prevent escape. A fully grown Amur tiger needs 9 to 10 kilograms of meat per day to maintain body weight, but after a large kill, it will often consume 30 to 40 kilograms in a single prolonged feeding. After feeding, the tiger typically drags the remaining carcass into concealment and returns over several days, a natural freezer provided by the sub-zero environment, preserving the meat. This is a crucial behavioral adaptation. The tiger does not hunt simply to eat immediately, but plans for storage, extending the value of each successful kill across many days. But even that caching strategy cannot protect the tiger from a threat. No prey animal poses competition from other species for the same kill. Ashuri brown bears, Amur wolves, and particularly raven flocks can locate and consume a tiger's entire cached kill within hours, erasing days of stored energy in a single raid. Camera trap data indicates that Amur tigers lose 15 to 20% of their annual food intake to scavengers and competitors, a significant subtraction from an already demanding energy budget. And of all those pressures, the greatest does not come from rivals or nature, but from something that changes far more slowly and far more quietly. The range of the Sika deer, the Amur tiger's primary prey, is contracting season by season as forest structure and snow dynamics shift across the Russian Far East. When prey becomes scarcer, the interval between successful kills lengthens and the tiger's energy equation becomes progressively harder to balance. This is what GPS data began recording from the early 2010s, Amur tigers gradually ranging farther, walking longer, and failing more hunts per winter than in previous decades. And here is where science discovered what almost no researcher had genuinely predicted: the Amur tiger's survival threshold does not flex. It has a hard limit. When prey density in an area drops below a certain threshold, the tiger cannot compensate by ranging farther, because ranging farther costs the energy it no longer has. This is not a vicious cycle, it is an energy trap, a point of no return that the tiger's own physiology sets for itself. Once a tiger's body crosses that threshold, no behavioral shift can save it, only an immediate successful kill can, and the odds of that become smaller with every passing hour. Ecologists call this the energetic depletion trap, and it explains why tiger mortality in the taiga often appears sudden, with animals that seem to be surviving found dead within days. Now, science understands the mechanism, but there is one thing that understanding still cannot fully explain. Why do some individual Amur tigers survive conditions that kill others in the same territory? GPS data from the Amur Tiger project shows that within the same zone, the same winter, and identical snow and temperature conditions, individual hunting success rates can differ by a factor of 3 between tigers. Researchers initially attributed this to age, but longitudinal data contradicted that assumption. 6-year-old tigers were sometimes recorded with lower success rates than 12-year-olds. Body size was examined next, but the largest tiger was not necessarily the most efficient hunter. Sometimes the opposite proved true. The answer has been emerging from an entirely new field of analysis: individual behavioral pattern profiling across extended time, and what it reveals has genuinely startled researchers. It turns out that individual Amur tigers develop personal hunting styles, and those styles accumulate over time like a form of learned experience that the animal refines with each successive winter. Some individuals learn to exploit terrain with extraordinary efficiency, habitually approaching from above prey, using gravity to amplify the power of their charge over shorter distances. Others develop technique for hunting in high wind conditions, using wind noise as acoustic cover, timing their footsteps to gusts that mask their approach from prey with acute hearing. The paradox is that these learned skills cannot be passed on because Amur tigers are solitary, and cubs separate from their mothers between 2 and 3 years old before the most demanding winters. Each young tiger must relearn from the beginning, often surviving 1 to 2 desperately dangerous winters before accumulating sufficient experience to stabilize its hunting success. With every generation, that hard-won knowledge must be rebuilt from nothing, in snow, in hunger, in darkness, with no teacher and no second chances. This creates a population-level vulnerability that ecologists call the generational bottleneck, and in the context of a small population, it becomes extraordinarily dangerous. Current estimates place the wild Amur tiger population at between 500 and 600 individuals, the vast majority concentrated in Primorsky, Krai, and Khabarovsk in Russia. This represents a significant recovery from a historic low in the 1960s, when only 30 to 40 individuals were estimated to remain a number but even at 500 to 600 individuals, each requiring 1,000 to 2,000 square kilometers of territory, The total habitat needed far exceeds any single existing protected area. This is what keeps conservationists awake at night, not the headcount, but habitat fragmentation. When the forest corridors linking territories are severed, the population fractures into isolated islands. When a population fragments into small isolated groups, genetic diversity declines, disease resistance weakens, and the capacity to recover from catastrophe fire, disease, extreme winter erodes rapidly. And here is where the picture becomes particularly complex, because the greatest ecological paradox of the Amur tiger is not cold, not solitude, but its relationship with humanity. GPS movement data shows that Amur tigers strongly prefer old-growth forest, yet they sometimes live closer to human settlements than any other large, dangerous predator species on Earth. Camera traps have documented tigers moving within a few dozen meters of occupied homes, and in many documented cases, both sides appear aware of the other's presence without conflict occurring. This suggests that the Amur tiger has developed a remarkable cognitive capacity, the ability to assess the relative danger and opportunity of human-adjacent environments with extraordinary precision. And from that extraordinary cognitive capacity, science is opening an entirely new layer of understanding, one that sees the tiger not merely as an apex predator, but as something far more complex. The Amur tiger is an ecosystem engineer. Each individual maintains just enough predation pressure on sika deer and wild boar to prevent both species from destroying forest regeneration through overbrowsing. When tigers disappear from an area, sika deer populations surge, and within years, forest regeneration is stripped bare, degrading the entire ecosystem from its roots upward. This creates a positive feedback loop. Healthier forest produces more prey habitat, which sustains higher tiger density, which maintains the forest, which produces more habitat still. The tiger is not simply a part of the tiger ecosystem, it is one of the things holding that ecosystem together. But the full picture is wider still, because the tiger forest the Amur tiger helps sustain is one of the largest carbon repositories on Earth. The Russian tiger covers approximately 1/5 of all forests on Earth and absorbs more carbon dioxide annually than the entire Amazon rainforest. When the tiger maintains the health of this forest by controlling herbivore populations, it is indirectly participating in the climate regulation of the entire planet. When you think about the Amur tiger, you are not simply thinking about a large animal in danger of extinction. You are thinking about a biological mechanism operating a climate system that we depend upon. Seen in that light, 500 tigers in the tiger are not a conservation statistic. They are a health indicator for a system vastly larger than any protected area or any single nation. Science is beginning to recognize something that reverses nearly every old conservation framework. Protecting tigers is not a cost. It is an investment in global ecological infrastructure. From that inverted perspective, the survival challenge of the Amur tiger is no longer the story of one animal. It is the story of a living system attempting to sustain itself across time. Every night, an Amur tiger walks its patrol in temperatures of 40 below zero. It is not simply trying to survive, it is sustaining something vastly larger than itself, an ecosystem, a forest, a portion of the climate system of the entire planet. And it does this not through intention, not through planning, but simply by being what it is, by continuing to walk, by continuing to hunt, by continuing to exist. This is something that none of the 8 billion of us are doing alone, holding an entire living ecosystem intact simply by the act of our own existence. Think about that when you recall the image that opened this, a creature standing in absolute darkness, hungry, cold, completely alone. That solitude, that patience, that silence, these are not tragedy. They are evolutionary qualities refined across 20,000 years of the harshest selection pressure on Earth. And that 40 below cold, you were asked to imagine at the start of this for the tiger, it is not an enemy. It is the environment it belongs to. The real question is not whether the Amur tiger can survive that cold. The real question is whether the world around it can hold together long enough for it to continue doing what it has always done. And the answer to that question does not live in the Russian tiger. It lives wherever people are making decisions about land, about forests, about climate. Tonight, as you sit in a warm room, somewhere in the taiga of Primorsky Krai, a tiger is walking in darkness. The temperature is 40 below zero, it has not eaten in 7 days, and it is still walking. No one taught it to do this. No reward waits at the end of the journey. Only snow, darkness, and 2,000 square kilometers of territory that must be walked. But as it walks, each footprint in the snow is part of something larger than any single animal can comprehend. It is keeping the forest alive. The forest is keeping the climate stable. The climate is sustaining the world in which you are sitting warm tonight. All of it begins with a creature standing in absolute darkness, 250 kilograms, placing one paw in front of the other, again and again, through the longest nights on Earth. The question was never whether it can stand in that 40 below darkness after 20,000 years. We already know the answer to that.